In this, the second lecture, we're going to examine the tools that environmental scientists have to bring to bear to help solve environmental problems. And we're going to use a particular case study as a way to look at our approach. For this chapter, you should be reading Chapter 2 on literacy in science and the process of science. And we're going to be considering problems with ozone in the atmosphere that were first noticed down in the Antarctic. McMurdo Station is a major research facility and set of buildings off the coast of Antarctica, and a lot of Antarctic research is based out of this region here. And it was noticed through studies and testing and monitoring at the time that an important gas in the atmosphere was diminished in concentration, and there was actually considered to be a hole in the quantity of ozone present, centered over the continent of Antarctica. So the question scientists were faced with, why was stratospheric ozone disappearing, and specifically doing so above the South Pole? To start off with, we need to consider what ozone is. You may have heard of it, but to understand its properties is important in terms of being able to know why its disappearance is of concern. You should be familiar with oxygen in the breathable form, O2, two atoms of oxygen bonded together, and ozone is a variant. It's a molecule of 3 oxygen atoms bonded together. It occurs naturally in the stratosphere, the layer in the Earth's atmosphere, and it serves a very critical function in that it shields the Earth's surface from incoming ultraviolet radiation generated by the sun. And I'm wondering if you've heard of other concerns about ozone in other parts of the atmosphere, especially if you live in or near major urban areas. And that would include situations in the troposphere, or the layer of the atmosphere closest to the Earth, where we occupy the surface. And when you have elevated ozone there, it's harmful and irritating to humans and other living organisms. It's a major oxidant, and as such is very irritating to respiratory systems. A common component of smog and other automobile exhaust components. And ozone is found in the atmosphere, as we noted earlier. It's a natural component in the atmosphere, and the atmosphere itself is a blanket of a complex of gases that surrounds the entire planet. As such, we find that the atmosphere is comprised of several layers, and each of these layers has different properties, including density, gas composition, and temperature. Shown here in this diagram, the atmospheric layers that we're most concerned with are the troposphere, down at the ground level here, and the stratosphere, which is the next layer up. As such, each of those layers has different conditions of temperature, pressure, and has a major influence on the role of ozone in that it's found in quantity, or greater quantity, in the stratosphere layer. On the right, the table shows the composition of the atmosphere in terms of its major gases, including nitrogen and oxygen, which we're most familiar with, water vapor, which is variable depending on whether you're near the tropics or in the drier polar regions, and then other gases. And we'll come back to especially to carbon dioxide and methane, nitrous oxide, later lectures when we talk about air quality. Ozone as well will be addressed, but our concern here is, even though that ozone is a very small component by volume of the atmosphere, as we noted, it serves a very important function of its interaction with incoming ultraviolet radiation. Incoming ultraviolet radiation is one portion of the electromagnetic spectrum. Radiation, electromagnetic radiation, is generated by the sun, travels through space, and reaches the Earth. and we find it over many of the different characteristic wavelength bands. We most commonly encounter it in the visible range, which is fairly small, but that gives rise to our ability to observe and detect colors. As you're all familiar with, there's a warming effect to the Earth that is related to the infrared radiation component as well as the visible. In the shorter wavelengths, though, there are ultraviolet radiation, X-rays, and gamma rays. And these wavelengths are so small that they are actually of concern in terms of their ability to impact and alter DNA, and as such, give rise to mutations. So these very short wavelength forms of radiation are of critical importance from a health perspective as they come into the Earth's atmosphere. In particular, and you may have heard reference to this by virtue of concerns over ultraviolet radiation, UVA and B are noted as the level to which various sunscreens protect against them. There's actually a third form or band of UV radiation, and that's the UVC. This is the shortest wavelength, it has the highest energy, and is the most harmful to living organisms were it to reach the Earth. Fortunately, regular diatomic oxygen molecules, O2, are able to absorb the UVC, and we don't detect it as reaching the Earth's surface. UVB is the next shortest, and that about 10% of it does make it through the stratospheric ozone that's present and does reach the surface. And this is the primary concern over its ability to stimulate or to cause damage to DNA, mutations in the skin, especially in the eyes, and the health effects we associate with skin cancers. Ozone, naturally occurring in the atmosphere, absorbs most of the incoming UVB radiation and prevents it from reaching the lower atmosphere and ultimately the surface. UVA is the lowest energy form of UV radiation, and it still factors into skin damage, aging of skin, can cause sunburns, and about 50% of it under normal conditions does reach the surface. And this is what, together with A and B, are the forms that most sunblock products are intended to prevent exposure to the skin. And as noted, the graph on the right, the temperature ranges change and are part of the distinction of whether you're in the troposphere or the stratosphere. You'll note, it's an interesting property, that temperature decreases as you go up in the atmosphere, which I think you're maybe familiar with. But once you reach the lower stratosphere, the temperature actually warms again. It's still below freezing, but it does warm until it reaches the top of the stratosphere, and then changes in the mesosphere and increases when you reach the outer atmosphere and are approaching space where there's very little effect of the atmosphere itself. So, other than the scientific interest in the change in ozone in the stratosphere and the changes in its ability to prevent UV radiation, we became concerned with the fact that increased UV light exposure has been linked to and correlated with a variety of health effects. Chief among those is skin cancers of various forms. The two pictures here are pictures of melanomas, which are the most malignant, most dangerous, and actually can be readily fatal on the skin. And they have very characteristic properties as far as the type of damage to the skin and the coloration in the raised areas. But there's also skin damage, skin aging with the non-cancerous forms of that. So over the last few decades, there's been recognition in the health community that skin cancers have been rapidly rising and throughout all parts of the globe. Another major area of concern is the prospect of the damage to the eyes associated with unprotected eye surfaces being exposed to increased UV radiation. This can lead to cataracts, clouding of the eye, which can diminish the vision. These are naturally occurring in a lot of older adults. And the loss of focus, or the ability to focus the eye through the fogging, and untreated, uncorrected, can lead to blindness. So we had the increasing occurrence of health effects, both skin cancers, eye problems, coupled with the observation by scientists that the ozone layer was diminishing, especially above the South Pole, but globally as well. And the connection of those two was the basis for a series of investigations that we'll address in the next couple of lecture segments. Now we turn to the process of how scientists investigate a problem like ozone's disappearance. And we'll focus on this case study of the investigation that started in the Antarctic to look at why the depletion was occurring and what the implications for influx of UV radiation would be. Solving problems like this and answering particular questions requires application of something I hope you're familiar with from previous courses. That's the scientific method. This is a bit of a review, I hope. Just to remind you of what science is. It's a body of facts and explanations, and it embodies the process that's used to gain that knowledge. And there are very specific requirements for the process of science to be valid. You should be aware, however, and always remember that the facts may change as more data is collected. An example would be that early on it was recognized that there was an increased occurrence of lung cancer by people who smoked. Decades before, there was an understanding of the chemical constituents of what were in the smoke that actually caused the cellular damage and led to cancer and other forms of lung disease. So as new data was accumulated, new understanding and explanations emerged, and a much better scientific explanation can evolve over time. Again, science is limited to asking questions and dealing with problems in the natural world. And that the physical phenomena of the world around us, both in the physical and biological environment, can be objectively observed, measured, and recorded. It's also key to note that these are the term objectively considered. Conversely, science is not subjective. It should not involve ethical or spiritual questions. A simple and almost trivial example is a question of what is my cat thinking? That's not something that can be quantified, directly observed, or measured at the current time. Observations, or measurements, which are our basis for detecting and understanding and observing things in the real world, is information that's gathered through our direct senses, and this is what the early scientists used. Later, different types of equipment and instruments and tools were developed that extended our senses. For example, we might know that it's the sun shining leads to an increase in temperature because we can feel that temperature. But with increased ability to measure accurately the temperature involved, we were able to have a much better basis of quantifying that temperature increase. Inference is the process by which we use those observations and develop explanations of what might have led to or caused the observed phenomena. And so we can infer through time and the detection of incoming radiation, electromagnetic radiation from the sun, of why temperature increases or why increased radiation levels are observable at the Earth's surface. This is the process of inference and working with the observations or data gathered. So to come back to our case study here, we can ask the question of what depletes ozone in the atmosphere, and recall from our first lecture section that that's occurring in the stratosphere. Scientists suspected that the key cause or culprit of that would have been a class of chemical called chlorofluorocarbons, or CFCs for short. It's a carbon atom bonded to 2 fluorine and 2 chlorine atoms. And these are artificial compounds made by humans over the last few decades. Their primary use is for coolants and refrigeration applications in air conditioners. In fact, if you're familiar with car air conditioners over the last decade, you might realize that they don't turn the air quite as cold inside the car as they used to. And that's related to the change of refrigerants in use related to the stratospheric ozone depletion. But Freon is a general class of chemicals that includes these CFCs. They're also used as dispersants in aerosol cans for sprays and things like that. And they're produced as a result of the production of styrofoam products. So, as you might guess from these applications, we're talking about the mid-20th century to when these were first introduced and put into widespread application through manufacture and use in technology and consumer products. So we come back to the question at hand of do the CFCs presence in the atmosphere cause the ozone depletion? So what are the observations we have at hand? We can state by measurement that the lower than normal ozone levels in the atmosphere have occurred over a span of several decades. This is the observation. The inference is what causes that reduction. And one reasonable one that was put forward was that the CFCs, based on their chemical properties, might be causing the ozone to disappear. So the way in which scientists used this inference was to pose a hypothesis, which is a tentative explanation that describes an observation. It's usually posed in the form of a prediction, so there is some sort of if-then statement based on the hypothesis. And some of the key attributes of the application of hypothesis and hypothesis testing are that the hypothesis statements themselves can be tested and they can be falsified. And we'll describe what that means. Our understanding in the process of science proceeds by whether or not we're able to accept or reject the hypothesis. And it should be noted and always remembered that you can never prove correct hypothesis. The hypothesis will be supported by observation or not supported by observation, but an absolute proof is not what's sought in the application of hypothesis testing. So there are some important considerations in the application of the scientific method and the use of hypothesis-driven science and experimentation. First, you have to always strive to make sure that the investigation or experimentation is unprejudiced. If you expect something to happen or not happen, you have to make sure that those beliefs or predictions don't affect how you conduct the experiment or gather data or observations. Objectivity is essential so that true observations and true hypothesis testing can take place. Another key requirement is that any experiments that are done as a part of an application of the scientific method is that they must be repeatable. I should be able to give my experimental methods to another scientist in another place, and they should be able to repeat my experiment and achieve comparable results depending on the nature of the experiment involved. A key component, as we noted earlier, is that the theory or a hypothesis must be itself falsifiable, meaning that there must be a condition where the hypothesis proves false. Errors that occur through the application of the experimental method or the instruments that are used must be recognized, minimized, and actually nowadays are pretty much quantified in terms of how much error is resulting from how you do the experiment. And it's always possible that unintended consequences can arise as a result of the experiment. The discovery of radioactive elements themselves was an unanticipated outcome of earlier investigations into the nature of chemical properties of early materials. Falsifiability is a situation where you have to have the ability for observational data that could prove the theory untrue. An example would be Newton's theory of gravity, which predicts the behavior of objects, depending on their mass, how they'll behave relative to one another. And this behavior can be observed and quantified. So it's possible that objects that do not fall, if that were to occur, could contradict Newton's theory and thus make his theory falsifiable. We haven't encountered those conditions to date, but it certainly could be a possibility in some situation or technology in the future. One humorous example is that of something that's not falsifiable would be a theory or hypothesis that there are leprechauns living in Bidwell Park here in Chico that read our minds and turn invisible whenever humans approach. Is this theory or hypothesis falsifiable? Why or why not would that be the case? I'll leave you to ponder that. So a review, again, of the scientific method is listed in this diagram, and it's in the book. I'm not going to go through it in detail, but the process of stepwise investigation, review, data interpretation, and it's also worth noting that nowadays, especially, publishing your results in a peer-reviewed journal is critical so that others may evaluate your work, repeat it, and verify it or refute it if necessary in order to perform the best science. So how do you test hypotheses? Depends on whether you're talking about an observational study or whether you're doing some sort of an experimental study. In an observational study, you would collect data in the real world. You don't have any way to really manipulate subjects or materials, and you can only show correlations. And this would be an example of what happened with the stratospheric ozone problem. There was no ability, since we're talking about a planetary scale atmospheric process, at least at the continental size, that you could manipulate, add CFCs or remove them to see what would happen to ozone concentrations. But there were, and there are, the ability to make correlational studies of that. Conversely, you can have an experimental study, and this is probably something you may be more familiar with through laboratory exercises or earlier science training in general education science you may have had. You collect data by manipulating variables. You apply different amounts of light to plants to see how they grow or don't grow. It could be watering of plants or various types of experiments where you directly manipulate one or more variables. You would typically have some sort of a test group and a control group to see whether the experiment and the variable that you're manipulating is having an effect that you hypothesize. And this does allow you more directly to show cause and effect. Correlation, as in correlational studies, is a situation where you have two things or more, but typically two things that occur together, but one does not necessarily cause the other. They're simply related. Cause and effect, on the other hand, is when two things occur together, but one directly occurs, the effect, in response to or a result from the cause or the manipulation or change that you impose during an experiment. All of these processes can lead to, through repeated experiments, can lead to the formation of a theory, such as Newton's law or theory of gravity, and that is a widely accepted explanation for natural phenomena, and it's been rigorously and extensively scientifically tested and is widely accepted. So to become a theory takes a test of time and repeated experimentation. This ends our second section of the lecture, and we'll move on now to the third. Now we'll turn our attention to how the scientific method, in its general sense and application, was applied to ozone depletion in the atmosphere. Again, Dr. Susan Solomon, shown here on the left at the Antarctic Research Station at the South Pole, is credited with describing the phenomena of the reduced ozone layers, which were later detected through satellite imagery and atmospheric sensing at the global scale, showing the lowest levels occurring right over the top of the South Pole. As we noted earlier, ozone formation and breakdown occurs naturally in the atmosphere, and it's the presence of the UV radiation that comes in and breaks the bonds of the O2 molecule that we're most familiar with into individual free oxygen atoms. Those coming into contact with the O2 molecules under the presence of the UVB radiation will form ozone. So in the presence of UVB and UVC, oxygen molecules are breaking and reforming their bonds to go between O2 and O3 ozone, with free oxygen atoms in dynamic exchange across the two. What happened, and this is occurring again in what's called the ozone layer, but ultimately it's most prevalent in the stratosphere. And it's the presence of that ozone then that restricts the presence of the UVB, or about 90% of it, from reaching the Earth's surface. What happens on the right side of the diagram here is that the presence of the chlorofluorocarbons changes that reaction process. The first step is that the CFCs are released into the troposphere by human activities, and they make their way up through atmospheric mixing and transition into the ozone layer of the stratosphere. Global winds circulate in the stratosphere, and a lot of this tends to concentrate these chemicals in the vicinity of the South Pole over Antarctica. In the presence of the UV radiation, especially the UVB, the CFC molecule is broken down, releasing free chlorine atoms, and those undergo a reaction in a chain-wise set of steps to combine with free oxygens and starve the formation of ozone. So it interrupts the formation of ozone, thereby reducing the amount of buffering or filtering capacity of the atmosphere to reduce UVB radiation from reaching the surface. So functionally, more UVB radiation than the normal 10% has been reaching the surface, leading to skin problems, increased cancer incidences, and eye damage as well. So there's a natural breakdown and forming of ozone that's interrupted in the presence of the CFCs. That's the primary cause. So what you should see if this process is going on is increased molecules of chlorine, single oxygen atoms being formed. So the hypothesis that was formed in a general sense was that the CFCs, through chemical reactions that interrupt the formation of ozone, are breaking it down and preventing it from reforming it. A prediction was that if polar clouds and sunlight were causing that chlorine to react with ozone, then increased numbers of chlorine oxide molecules should be found in the atmosphere. But it's appropriate to ask, could there be other causes than CFCs that cause the ozone depletion? And these would have to be investigated as well. This chart showed earlier shows the ozone concentrations declining over the last 50 years and in correlation with the increased concentration of chlorofluorocarbons, especially 12, in the global average. We mentioned earlier that during experiments that there are various types of variables in describing this. An independent variable is the factor being manipulated. The dependent variable is a response of an organism or property or characteristics that's being measured. So for example, you could have a plant experiment where The plant is the plant growth, say, is the independent variable that's being manipulated. The addition or lack thereof of water, for example, would be the dependent variable, and the independent variable would be the water. The dependent variable would be the growth or survival of the plant. And then a control variable would be other things that are held constant. So say under the plant example, you would have light being held constant on all plants. So again, the factor being manipulated could be applied water. The dependent variable could be the amount of growth, and the control variable might be light or temperature or some other growth factor that the plant also requires. This example. In the experimental process, you can also have different groups. The test group that's being exposed to some manipulated variable, and a control group that's given a standard application of, say, water in our example. And that's the baseline. So under normal conditions, the plant grows with to a certain degree with normal watering, and if you add more water or less water, then you might predict some other type of response. It's also important to replicate this so that you don't have some unknown variable or situation that's causing an outcome that you can't otherwise describe. The replication process just means that you're going to repeat the treatments, including the controls, and typically you would repeat the experiment, conduct it many, many times as a basis for drawing a final inference. But how do you know if your groups are really different in terms of applying a treatment? It's important to apply the discipline of statistics, and this allows you to quantify and determine whether or not there are any differences between the test and control groups, say in the case of the watering experiment, after a certain amount of water has been applied. In any event, we can't control for all variables, and so it's important to assign a level of certainty to our conclusions if we conclude that more water equals better plant growth, for example. In statistics, you'll see reference to a probability value or p-value, and that will determine whether or not, or the extent to which you can conclude that there's a difference between the treatment and the control groups based on the experimental application. Typically, scientists will assign a 5% or 0.05 level of significance. What this means is that quantitatively we've accepted the fact that if we perform our experiments correctly, then we can be approximately 95% sure that our conclusions are correct. And that comes down to an acceptance of how much error in the interpretation are you willing to risk. And that this probability that you want will probably vary with how important the outcome or the test itself is. So, is ozone depletion and increased exposure to UV radiation causing higher rates of skin cancer? That's a fair question, given the fact that we see that there's ozone is being depleted, there's more UV radiation coming in, and there's increasing rates of skin cancer. So how do we go about testing this? There are different types of studies, and some of these, when they involve human situations, have different ethical considerations. An observational study, one of many that was done, predicted that the incidence or the frequency of skin cancer should be higher in those areas where the ozone depletion is the highest. This could be in Antarctica, but not many people live there. So the other areas that were looked at were Australia, especially the southern coast, and in the Patagonia region. And what they found is that with increased exposure to more radiation in that period, in those populations there was a higher incidence of skin cancer. And the experimenters concluded that living close to the hole in the ozone layer near the Antarctic increased one's chances of developing serious skin cancer. The other type of study that can be done, you can't really do on humans for obvious ethical reasons. You can't expose people to elevated levels of UV radiation because you'd be elevating their risk of skin cancer and potentially death. So instead, researchers have looked at, under experimental application to lab animals and to determine whether or not there were increased cancer in mice with greater exposure to UV radiation, and particularly UVB. So they divided the group up into test groups with a control, and then assigned those that were exposed to elevated UVB and those were exposed to normal levels, and they found that 100% of the mice experienced skin cancers with that increased exposure. And given that mouse skin and human skin has enough comparable characteristics to it, the experimenters concluded that the UVB at the levels seen in these areas around the hole in the ozone layer, meaning the south polar regions, caused skin cancer in these mice, and likewise was not a sure cause and effect for human incidence of cancer increase, but certainly is suggestive that humans would be at greater risk by the levels that we're being exposed to with the result of ozone depletion. That concludes our third part of the lecture. We'll move on now to the fourth in the next segment. So in our final segment, we'll look at how do we solve the problem associated with ozone depletion by virtue of the way we introduce or reduce our introduction of CFCs into the atmosphere. Once the problem was recognized, governments started to take action, and they recognized the threat to human health through the increased skin cancers. And in 1987, the Montreal Protocol was adopted by participating countries. The United Nations organized and convened the meetings to set this up, and they developed a plan to phase out use of chlorofluorocarbons. From 1987 to 2009, virtually every country had signed the agreement, and governments developed their own policies for the reduction of CFC production and use. There's a very interesting timeline that took place following the Montreal Protocol. The initial commitment by countries in 1987 was to scale back CFC production by only 50% in the year 2000. So in 13 years, global production and use would be reduced by 2000 was the original goal. 3 years later, countries passed an amendment to completely phase out ozone-destroying chemicals by 2000. Only 2 years after that, and 5 years after the original agreement, an amendment was passed to completely phase out ozone-destroying chemicals by 1996, less than a decade later. And if you think about this as a global agreement and a global set of actions, you might wonder why there was such a rush following the initial protocol agreements. Well, one need only look at as the policymakers, decision makers, and even the businesses did at the time, that on the two charts below, you'll see that the rates of malignant melanoma between 1973 and 2004 were steadily climbing. And the time span over this, both in male and female, was catching the attention of policymakers, that these are rates that of a disease, that a form of cancer that result in fatality. The lower right figure, comparable rates, show that there was likewise an increase in European rates in the UK. Okay? So now we're not talking about just a phenomena that's going on over the Antarctic and affecting most commonly the peoples living in the south of Australia and the southern tip of South America and the Patagonia region. These are small, relatively sparsely populated areas. Now we're talking about a global reduction in stratospheric ozone, and that was resulting in northern hemisphere mid-latitude cancer rates. And that caught the attention as being a clear and present health danger that prompted this rapid increase in action. What we saw on this is that policies were established and passed, and these translated the valuation of protection of human health into action, and the U.S. banned CFCs in certain products back in the 1970s, and then adopted the accelerated rate of reduced use over the time span of the Montreal Agreement. It was somewhat easier here because there were quite a few good alternatives of refrigerants and other chemicals, so these were not necessarily difficult transitions. There was an expense. Detroit and the automakers had and passed along the cost of several $100s of retrofitting and changing out refrigeration, air conditioning units in cars. So there was a cost, and these were passed on to consumers, but they were viewed as being more than offset by the production in human health. So in 1990s, the U.S. started phasing out the CFCs entirely, and it was, again, somewhat of a unique cooperative effort between industry with public acceptance and government motivation to find solutions to this problem and come up with alternative products that allowed us to keep the uses of refrigerants that we want for the purposes we use them for, but not at the cost of human health. This is an example of a precautionary principle that you might consider in the current day and age. Even if you're not 100% sure, and given the correlational nature of the studies of, and even in simple mouse-based experiments, of exposure to UV radiation at the levels increasing around the South Polar region, there was still enough of a risk that the society decided to take a cautious approach and change, and that the prospect of doing nothing and keeping business as usual with CFC use, the risks were much greater than the perceived alternatives. And so action was taken, again, with the start of the 1987 protocol was enhanced by virtue of the studies by Susan Solomon only a year later, which provided scientific support for the concerns of how the chlorofluorocarbons might be reducing stratospheric ozone. This is an example. This whole process that was gone through on this is a process of another important approach, and that's called adaptive management. This is where you develop a plan that allows you to adapt alter your strategies as new information comes into being and is made available, or the situation changes. And again, the case of the Montreal Protocol was deemed not sufficiently accelerated enough of change, especially in light of the scientific explanation provided by Dr. Solomon's research. If you look at the projected future conditions with the abundance of chlorine in the stratosphere, if no protocol had been reached, the levels would still be rising over the time span and into the near future in the next couple of decades. The original Montreal Protocol would have reduced the rate of increase, but it would still have had it increasing over much of the century. The 1990 amendments and the total phase-out starting there still had an increase over the century, but at a much lower rate. And it's with the 1992 and more recently 1999 amendments that have drastically reduced the levels, and it's projected that the peak, which is probably we're at or near the peak of the chlorine levels in the stratosphere, that those will diminish readily through the century and show a recovery of stratospheric ozone back to pre-industrial or pre-application levels. And this goes back to this observation, this correlation we found between ozone depletion, CFC use, and that there was a time to act on this that was employed, presumably in time, to prevent large-scale and even more catastrophic health effects. The projections in the future, it means that we're not completely recovering yet. Last year, 2011, it was observed that the largest ozone hole ever, meaning the greatest depletion of ozone, had occurred above the Arctic. And this again has implications for the northern hemisphere and the fact that the CFCs and chlorine constituents do migrate in the upper atmosphere around the globe and now are affecting the Arctic region as well as the former concerns in the Antarctic. It is projected that with the current protocols in place that the mid-latitude areas in the north and south hemispheres will be back to the pre-1980 levels by the mid-century, and that by 2075 even the polar regions should be recovering back to the levels of 1980 or before. Ultimately, a complete reduction of these will probably take several decades longer to get back down to more trace quantities. Dr. Solomon noted it's clear that ozone will ultimately recover, but it's also clear that it will take many decades to do so. So this suggests that there is a risk that you face and probably your children face in their exposure to enhanced UV radiation levels by virtue of the residual, although declining, depletion of ozone in the stratosphere. So what I would like you to do is to pose a hypothesis describing the rates of skin cancer over the next 40 years. And then consider what sort of risks you and your children face over that time frame. There's still a culture, or we still as a culture in the United States value that suntan look, but it comes at a significant health risk with exposure to enhanced UV radiation and the cancer forms, especially the malignant one, melanoma, and still serious basal cell carcinomas, present grave consequences for those folks that still seek that suntan look through exposure to sunlight. This concludes the second lecture. You should prepare for and complete the second quiz, and then move on to the third lecture.